My name is Jordan Yates. I'm a co-founder at Embeint. Before we all get too bored, we've got a booth downstairs if you want to come talk about anything you see in the talk. And this presentation is about CPatch, which is optimizing over-the-air upgrades through binary diffs. So what is the problem that we're trying to solve with this? So increasingly through regulations and just general customer expectations, firmware upgrades are a must-have these days. You can't just shove out a product into the world and let it run there for the next 5 years. There will be feature updates, security patches, etc., etc. And firmware updates, as much as we would like them to, they don't just magically appear on a target device when you hit build or deploy on GitHub. And because they don't magically appear, you have to get the updates to the devices somehow. And in many cases, the only options for this are, well, your devices are wireless, which means that you need to send this data over a wireless communications link. And different links have different limitations. It may be a low bit rate, which, for example, LoRa, so it might take you a really long time to send a large firmware image. You might be paying per the kilobyte for something like LTE, so the larger your images are, the more it costs you, and that scales out with the number of devices you have deployed. Your communications link might be quite energy intensive, for example with satellite communications, so the larger your images are, the more energy it takes to send or receive them, drains your batteries, degraded performance. And it might be just uptime or like literal availability of the devices you're trying to update. So got a nice picture of some cows here. Cows like to walk where they want to walk. They don't stick around near your gateways. So you may only have a certain amount of time before the cows will wander off and you've lost your chance to update. So what if instead of sending the entire image when you have a new update, what if you could send 25% of the image or 2% of the image and still get your new firmware running on your device with your new features, with your bug fixes, etc. So what does a solution like this look like? Well, so what are we taking advantage of? And in general, what we're taking advantage of is that for any firmware version n+1, it's basically going to look very similar to version n, right? There's going to be some small changes, your bug fix, your security fix, whatever it is. More concretely, but I'm sure still not mathematically correct, you have vn+1 equals vn plus some small difference, whatever that difference may be. And the key point here is that, oh, that is the wrong button. We already have vn locally because you're already running the firmware version that you currently have. These pointers are hard. All right, so what if instead of sending the entire image, we can just send that some difference, the patch? So the question you might be asking is, hasn't this been done before? Yes, several times. There are quite a few of these binary libraries out there. Some of them you may be familiar with. There's BSDiff, there's XDelta, JoJo diff is, at least from my experience, the most well-known in embedded circles. And there's others as well. But we think that we have some tricks to make this more efficient. And each of these has their own sort of downsides. So BSDiff, for example, it compresses the diff files. So before you can apply the patch, you need to decompress it, which can be challenging on an embedded device. XDelta just gives huge diffs for whatever reason. JoJo diff, it's GPL, the patch generation is C++. There's some things with it. But there's also a lot of sort of string-oriented diff libraries, so for diffing like text files and stuff, which is great if what you're working with is text files, but in this application, what we're interested in is embedded binaries. So what am I sort of ignoring or papering over in this talk? So I'm ignoring, once we have a patch file, how do we get it onto the device? That's outside the scope, LTE, Bluetooth, whatever. What has happened here? Oh, it's back. How do you know which patch file to send? So if you're sending a patch, you need to know what image you're currently running. Ignoring that for now. How do you know what exactly the contents of that file, of that version is? Ignoring it. How are we loading the new image? Don't care for the purposes of this talk. And what are we assuming? Well, to be able to apply a difference to a firmware version that you're currently running, the original image has to be readable. Now, 5 years ago, this may have been sort of self-evident. There's more caveats these days with stuff like TFM, which the previous talk was mentioning, where secure images might be read protected. So you need to be able to read the original image to be able to apply a diff to it. We're assuming the original image does not modify itself, so no generative programming of erasing flash pages and writing new application code, with the one caveat there that the MCU boot trailers do modify themselves when you do an upgrade. So there's things you have to take into account there. We're assuming that it's a contiguous image space. There's no huge gaps in the image for whatever reason. Maybe there's some magic microcontroller that I've been talking way far away. Maybe there's some magic microcontroller where there's large gaps in the image space. We're ignoring that. And we're also ignoring link time optimization. So I know that LTO can do a lot with rearranging images for even very small changes because of the optimizations that it's trying to apply. So CPatch, what is it? Well, what makes it different in this case? So CPatch is written, it's focused on the embedded patching side, not on the patch generation side. So we're focusing on things like linear patch file and output file access, so you can just read from the start, read to the end. There's no jumping around. Same thing with the output, because if you're writing in a linear fashion, you can take advantage of stuff like the flash pages. They need to be written in blocks, etc. All of the memory used by the library is it's constant, it's compile time, and you can configure it if you want to improve buffering, etc. The patching has built-in file validation, so you can validate that, hey, this patch you've sent, it matches the version currently running. You can validate that what you've generated at the end is correct and that the patch file itself is not corrupted. It has a native Zephyr implementation because that's really what we care about, whereas some of the others have like these file system, like you try to implement fopen, fread, fwrite, etc. for to interface to the generic implementations. It's single step patching, so there's no decompression step or anything before or after. You just read the file, read the patch, apply it, you're done. And it's really trying to be as simple as possible on the embedded side in terms of how much ROM does this implementation take up. We want it to be small, leave lots of space for application logic. Again, different from sort of the other patching stuff that we've seen. We've got the patch generation is all done in Python. Makes it really easy to do stuff like dictionaries and hash tables and stuff. It's got a fully featured standard library rather than C. Makes it really easy to implement the patch generation and just whip up a new strategy for generating the diff and test it out within half an hour rather than fighting with a compiler to test how that works. And because we're generating diffs for embedded applications, the file sizes are generally small. The efficiency problems of Python don't really matter in this case, whether it takes 100 milliseconds or 500 milliseconds, you don't really care for this use case. So jumping a little bit to how CPatch works and what it's sort of taking advantage of. So what makes binary diffs feasible in the first place? Well, the first thing is reproducible builds. So if you couldn't just build the same application twice and get the same application image, then you have no guarantees that just changing some small part would give you something that looks similar to the original. So reproducible build is sort of the first stepping point. And the other thing we're taking advantage of is that, as mentioned earlier, most of an application doesn't change. You're fixing an off by one error. You're changing an LED. You're adding some new whatever it is that your application does, but most of it is doing the same thing it always was. So what makes it challenging? Well, as we can see over on the right here, I've got a little bit of a high-level view of what a binary might look like. Changes early in the file, so up here, affect everything further down. So as a piece of memory at the start might expand, all these memory addresses of the rest of your file are also changing. So changes aren't necessarily self-contained to where the change applied. It ripples through the file. And this primarily affects sort of absolute memory references. So if you're just referencing with respect to the current program counter, nothing really changes. If you're trying to reference from early in the text to somewhere in the .data, that's gonna change. There we go. So just as a brief sort of example of that, if you've got this super simple binary file, you've got some text, some functions, and they're taking pointers to functions or data. You might have a function with an absolute memory reference, something which is relative, so it's just relative to itself, and then another one that's referencing further down. So what happens to this if our very first function in our binary, f0, is now larger for whatever reason? You fixed a bug, etc. So f0 is now bigger. The entire file as a whole is now bigger. The relative memory addresses, I've actually messed this up, that should be negative 30. If that was f1 instead, that would still be negative 16. But the absolute memory addresses have changed. So even though it was just fn, f0 that's changed, f1 and f3, the contents of that file, or the contents of those functions have also changed. So hopefully that's at least a little bit, maybe readable. So this is just a list file from a random application that I have, and I've just looked at a random function within that file. Now, and this is a diff between two application versions. Now, on the left here, if we haven't seen list files before, is the absolute memory address of the various instructions. So we can see that all of those are changing, as we would expect from this function now living in a different point in memory. But we can see that most of the instructions, for example, well, the instructions have all stayed the same because this function hasn't changed across the binaries. But if we look down the bottom here, we can see that this memory address here has changed. My screen is even smaller than that, so I can't actually read what changed there. But I think it's referencing data somewhere. So between these two versions, most of the functions stay the same, but there is this little bit here which has changed, even though we've done nothing to the function. So in practice, the data structure, the data section, which is holding your compile time constant initialization for values, typically copies pretty well because it doesn't matter where you shift that in memory, the values are still going to stay the same. But in the .text function, in the .text section, where you have all your program, ROM, etc., it's going to be much rarer to have huge runs or identical bytes. So what you're normally going to see is you have sections where the bytes all stay the same, then 1, 2 bytes changing, then another short section where it's the same, a few bytes changing, etc. And spoiler alert for later, this is sort of what we're taking advantage of with CPatch. So how do we encode a patch? So conceptually at a high level, the metadata about instructions sort of drives how efficient that your patching ratio is. So in a magical world where you didn't need to send any metadata, your patch could just be a list of memory addresses where this byte exists, and you just look for where that byte is each time. And because there's no metadata about where that byte is, you've got a patch in 0 bytes. So at some level, the amount of metadata that you have is driving the compression ratio. Which also means that the fewer instructions you can encode this as, the better your patching ratio is going to be because you have less overhead from the metadata. And jumping back to the previous slide, how can we efficiently encode this difference pattern that we observe in real embedded applications. And finally, how can we make as much information as possible implicit rather than explicit? Because implicit information is information that you don't need to send, which again helps with the overhead and the metadata, etc. So in terms of making as much implicit as possible, because we want our patch read and output write patterns to be linear anyway, the pointer to where you are in the output image is always implicit, because after you've written 16 bytes, your output image pointer is now 16 bytes in the future. You never need to send what part of the output image you're actually trying to reconstruct at this point here. Similarly with the patch data pointer, because the patching is written as just a list of instructions you execute sequentially, you just read bytes from the patch file. There's no caching of the patch file. Once you've read 6 bytes of patch file data, your patch file pointer is 6 bytes in the future. So both of those things are always implicit. And then we've got the input image pointer. So where we're currently trying to copy data from, because copying is the most efficient operation, because if your image is the same, it's just one big giant copy operation. So we implicitly start at 0. That saves us one operation, I guess. But then all the other operations are implicitly incrementing this pointer. So if you have a copy 16 bytes from X, and then 2 bytes have changed, and then another copy instruction, that's implicitly going 18 bytes after the start of this little sequence. So this is encoding that the pattern we saw earlier of bytes staying the same, small change, bytes continuing. Because it's implicitly incrementing, we don't need to send any, we don't need any extra instructions to encode that. But obviously, in a real application or a real diff, it's not always going to be nicely linear. So there are instructions to update the input image pointer to point to some newer location or some other location in the input file. So we've got a bunch of instructions for CPatch. Because we're focusing on simplicity, they are quite simple. We've got copy bytes, so copy from somewhere in the original input file to the output. We've got write new bytes to the output. We've got our 2 shift instructions for shifting where the input image pointer currently is. And then we've got the patch instruction, which is the CPatch special, and where we try and improve the efficiency through the observed patterns that we see. Actually encoding this into binary, we've sort of got this variably sized instruction header where the first 4 bits are an opcode, and then you've got some arguments for that opcode, and then things are a bit packed just to try and encode as much information as possible into various instructions. And you've got different variants based on how much data you're copying or writing or shifting the address by to try and save the bytes as much as possible. So what is the magic patch instruction? So the goal of the patch instruction is to encode short runs of copies and writes so that it can efficiently handle the absolute addresses shifting. So if in the original file we have this array of data, and in our new application image we've got 3 bytes of the same, 2 bytes different, 3 bytes the same, another byte different. We want to try and encode this as efficiently as possible. So we have a patch instruction which, instead of requiring an opcode for every single little piece of this, it's implicit that the patch instruction is encoding a run of different instructions, and you can find the end of that by a terminating byte at the end. So the encoding is essentially how many bytes do we copy? That's just a single byte. Then we've got how many bytes of new data do we have? followed by the data that we're writing, another copy instruction, I'll get back to the special thing here, and the byte to change, and then the terminator for the end of this larger patch. What we have observed in practice is that a lot of real patches have n bytes of copy, 1 byte changed, n bytes copy, 1 byte changed again. Now, if each of these copy and writes was done as a just naively, then each of these 1 byte writes would take 2 bytes of patch data, right? One for the opcode or the metadata, and one for the actual byte itself. But what we've figured is that by sacrificing one of the bits in the copy length, you can signify that, hey, this next write, after this copy, we have a 1 byte write. So we can apply the copy, copy in the 1 byte, and jump straight to the next copy instruction, which saves a byte, but with a real application where you have hundreds or thousands of these operations, that translates into kilobytes of savings. So again, because this is all done in Python, it's really easy to just remove steps of the encoding process and see how it affects what happens. So I've got graphs on the next page, but just for a comparison of how much of an improvement we can get from this sort of patch encoding, if we just drop the patch instruction entirely, we might get a diff file of, say, 64 kilobytes here. But if you encode these efficiently with these runs, you can drop the patch size by almost 20%. This is just a random application. It's relatively complex, but yeah, so it does lead to real savings. So how does this compare against the other options which are available? So this is essentially generated patch files across for different algorithms for updating a given application across multiple versions. The application itself is quite complex. It's a NRF 9151. It's got trusted firmware M. It's got LTE libraries. It's got Bluetooth. There's a lot going on, and the entire application, the original application, is 568,000. I can't divide by 1,024 in my head off that. So for small changes, like down here, we've got diff files of like 16 kilobytes. I did have slides with percentages here, but I've lost them apparently. And so obviously the size of the patch file is going to depend on how much has changed between the different application releases. For example, we can see here that version 1.3 has quite a large diff, but that's because that version was jumping from Zephyr 3.9 to 4.1. So even with an update of the core operating system across 2 versions, the patch file is, what's that, 120 kilobytes compared to 570. So even with that huge jump, and I think there was other features in there as well, the entire patch file is still only 20% of the entire image that you're sending. And Zephyr doesn't update from 3.9 to 4.1 very often, right? So these are the sizes to jump from 1.111 to 1.2 to 1.21. If instead if you're just trying to jump to the latest version, we see a different pattern because to get to 1.31, it's a small jump from 1.3 and then larger jumps if you're running on some older version. But the diffs don't explode, right? Like whether you're running 1.11, 1.110 or 1.111, it doesn't really make a difference for the patch file. So even when you're jumping from much further than 3.9 to 4.1, the diff files still don't explode. They're still delivering you sort of meaningful savings. And I guess just comparing the 4 algorithms we have here shown, so we've got CPatch in the red, which for all of these, the relative encoding, or the relative sizes are about the same. So CPatch is generally, is second best in terms of size. As I mentioned at the start, BS diff is essentially running like a zip file over the patch file. So if you want to actually apply this diff, you need to first decompress it and then apply it, which means the implementation itself is more complex, takes up more space in ROM, etc. Jojo, we're always quite a bit better than Jojo diff, and X delta is just always bad for, I don't know why. But yeah. Right. So in addition to just the patch file data itself, we have a header on that patch file, which is used for validating everything. So we've got some magic number at the top. Make sure this file is actually a patch file in case this is being stored in shared memory somewhere. We've got validation of the input and the output sizes. So we've got the length of the field we're looking at and what the CRC is expected to be. And another field down here which validates all the previous information in the patch file. I haven't seen corrupt patch files on our devices, but it's nice to know that if they are there, it'll be caught, they won't try and apply. Even if they were, it wouldn't be the end of the world because MCU boot would still sort of catch it and go, hey, the signature is bad, but it saves you the whole rigmarole of switching the image states, running through MCU boot, rebooting the device, etc. So what does the Zephyr side of this look like? So it's generally pretty simple. The code is probably not super readable, but that's the core loop of the patching. To start with, you perform your validation of the input file and the patch, so you know that, yes, I'm running what I expect. Yes, the patch file isn't corrupted. While there is patch file remaining, fetch the next opcode, execute it, run some callback so you can tickle all your watchdogs because you don't want to reboot halfway through your patching process. And that just runs in a loop until there's no patch file left. At the end of that, you flush whatever might be sitting in your buffers and then read back from the output flash to go, hey, yes, this matches what I was expecting from the patch file header itself. So you go, yes, this patching worked, and I should try and reboot into it. Yeah, that's just a graphical version of the code. So as I mentioned at the start, it's a native Zephyr implementation. There's no weird OS abstraction shims sitting in there. And it really just builds upon two of the core Flash abstractions. So we've got stream flash writer, which is just a way to push individual bytes into a buffer until that buffer fills up, and then you write the entire buffer to Flash at once. Because writing a 4 kilobyte page takes about the same time as writing a 1 byte thing. So you want to write aligned to page boundaries as much as possible. And then all of the reading and all of the reading from the various Flash areas is all done through Flash map. And we've added a little custom, wrong button again. We've got a little CRC compute helper, so you can give it a Flash area and a size, and it will compute a CRC over that without needing to manually run it yourself. There's links to the Zephyr docs on those two areas if you're interested. So once the patch has completed, this is diving a bit into the what happens afterwards step. We request the bootloader to upgrade, and then we actually do the reboot a few seconds later. The reason why we do it this way is that in our actual applications we have some sort of flags that are set when we trigger a delayed reboot, so that various tasks, etc., have a chance to shut down properly, shut down the LTE modem, shut down tasks that are running, etc. Just gives the application a bit more of a chance to cleanly shut down rather than killing its power, essentially. Where are we at? 150. So on the Python side, so on the generation, we essentially generate a whole bunch of different patches and then just choose the smallest one. The generation is all heuristic. Make no claims that this is the optimal solution for this, but as long as it generates the same output instruction set, we can play around with it at a future time and see what new approaches can result in smaller patch files. And yeah, efficiency is sort of secondary, so it's not the optimal patch, and it's certainly not the optimal way of generating the patch, but it's fast enough. So the first step is we sort of make a naive diff. So we have a hash map of the original image. We search through that to find, hey, where in the original image can we find this section of the new image? And we find the longest match there and say, hey, okay, great. We'll copy 3 kilobytes from that memory address. And if we can't find somewhere in the original image which had that data, we add it as new data. What we see out of that is a pretty common pattern where we shift the address by some number of bytes, copy some small number of bytes, and then shift back by the opposite amount, which generally indicates one of those like sections where you've got bytes the same, a little bit changing, and then bytes the same again. So we actually just sort of get rid of that. We just replace that all with a single write, with future steps in this generation optimizing that. The next step is to sort of prepare for this patch instruction. So the first step has some minimum length for finding copies. Like you don't want to try and find a 2-byte run somewhere because the amount of, when you encode that patch, you'll spend 5 bytes encoding the address shift just to copy 2 bytes when you could have just written the 2 bytes in the first place. So first we sort of crack these single write instructions into writes, copies, and then writes, which gives us the right structure for us to apply the patch file to later. We make sure that we're copying at least 2 bytes because otherwise the metadata is larger than the space you're saving. And this can crack a single write instruction into an arbitrary number of these sort of patterns, which we see in practice. This is currently the most complicated step. There's quite a bit going on there to make sure that you don't accidentally break the patching file, patching stuff. Then we've got the merging step, which merges runs of copy write into that patch instruction. So it then compresses all of it down to a single instruction. And then you've got the post-generation output, the post-generation actions. So at this stage, these are all just Python classes which are the generic copy n bytes. So we then specialize those into the various length-specific versions, convert that into the actual binary representation, generate the patch header according to the input and output files and the patching. And then from that generated binary file, we actually feed that back in with the original image file and go, great, can the Python patching algorithm reconstruct the output from just the information that it has? So you can make sure you haven't saved some extra data in the Python classes somewhere which you're using, which the embedded side won't have access to. So I've got a little bit of a demo. I don't know what time this is supposed to finish, but we'll keep going until someone says stop. Right, so for this demo here, I've got my laptop here. It's running some Python tooling. We've got the magic of Bluetooth Low Energy, and on here I've got three devices, Cortex M33s, NR54 L15s. They've got some LoRa chips on them. What they're actually doing doesn't really matter, but it's not it's running a real application. It's not running a hello world or anything. So on the software side, we've got obviously the topic of this talk, CPatch, running on the embedded side, but there's a lot of other stuff which comes into what I was ignoring at the start in terms of how do we know what data, how do we know what version is currently running, how do we know which patch file we need to send, how do we send that to the devices, how is the patch applied, but obviously you need those parts to actually have a demo. And that text is going to be unreadable, isn't it? Yeah, okay, perfect. So what this is showing is it's a generic logging application, and what we've decided is that it's a bit boring. Instead, what we want is we want a little dance party on the LEDs, so we just want to randomize the LEDs in this new version. So none of the core functionality has changed, but in our main loop we now have LEDs blinking randomly. So if we jump out of this, jump to the terminal. Oop, spoiler alerts there. So another thing we're sort of ignoring, how do we know, how do we version our applications, etc. We have a tool which generates the diff between different versions, so we'll just run that. So for this particular application, from version 1 to 1.1, our original file is 400,000 bytes. Our patch file from adding the LEDs is 24,000, so the patch file is about 6% of the size of the original image. And that's made up of 1900 instructions, and you can sort of see the distribution here of what instructions were generated. And as we would sort of hope, this patching is the largest number of instructions, which is good, because it means that our generation at least is doing what it's supposed to do. So up in the top window here, I've got a Bluetooth listener, which is just using the native Bluetooth stack from the MacBook. It's not the greatest, but it works for demo purposes. So we now have a patch file, and now we want to tell our tooling, hey, great, we want to update these devices to version 1.1 because they're currently running 1.0, doesn't have our nice LEDs. So we'll start that. Well, it's already done one. That's someone bought a device that is running an old version. That's probably, yeah, Phil's got a version there, but I mean, that shows a nice little thing. So it's seen a device that it doesn't have a diff for, so it's like, oh, can't try and update that. But essentially it's listening for versions that the devices are broadcasting. It goes, hey, sweet, I have a diff version 1.0. It connects to the device, uploads the patch file, and then disconnects. In the background now, these guys are going off and actually applying the patch file, running MCU boot. There's no point on our side to just sit there and wait for it to finish on that one device before we start others, because there's other devices to update. And essentially, the script just continues sitting there, waiting for new versions to be reported. And we can see that it's seen the new version being reported from the 3 devices. And running, well, similar theme for the rest of this talk, you probably can't see the LEDs. You can a little bit. If you can't, you can come up closer after. But yeah, so our devices are now running our little dance party. And I mean, this will just sit here forever because it's still looking for new devices. But yeah, that's the demo. Yeah. So, any questions? I don't know how long we have for questions, but I'm going to go left, so that first. So yes, yes, it can. One of the things which we used to do is you can order the link, you can order the output, you can order different sections from the binary according to what you think will change least. So if you put the things which will change least often at the top of the image, it means that they won't change, like that they can essentially be encoded as nice big long copies in your patch files. Adding buffer between the data and between the text and the data also does that, because it gives you a little bit of room to, if your text section increases by 16 bytes or whatever, none of the data addresses change. That helps as well. I can't remember whether we still have the padding between the text and the data, but we stopped doing the individual linker sections because each Zephyr update tends to change the name of libraries, and keeping it all up to date is a bit of a pain. You can get extra efficiency out of that if you're willing to do that. My pull request, which made it easier, went stale and closed, and is what it is. Yep.
Is it correct to say that one of your assumptions is that the image on the flash is not encrypted because it has to be signed by the user? Because if you use encryption, I guess the binary diff will be, you will save nothing, right?
Correct. If the new image is encrypted, well then, yes, it's essentially random data. You're not going to be able to generate a diff between those two things. I'm not aware of any applications which have encrypted images that you're currently running, because I don't know how you'd run an image which is currently encrypted. But yes, if your new image is encrypted, this won't work so well. But neither will the other patching libraries. Colors. Yes, there's no, you can't do it in place because you are still using the current image when you're generating the new image. So it requires the currently running image slot, so slot 0, requires the image slot for the new application, slot 1, and then it requires some extra flash storage for the patch file itself. For our applications, we have a sort of like a generic flash region which we use for this and other purposes, depending on what's actually happening at the time. So it's not just dedicated to this. But yes, you need a third small slot. Now that does limit, if your patch is too large, then it won't fit in the patch slot. Well then, you can't run the patch. And your options then are to either do like a semi-upgrade to a closer version, which it will fit, or just use a full image update for that one jump.
Why do you do sort of patching flash?
So you could apply it, you could stream it, you could apply it as you receive it. What that would mean that you have to, the patching process itself is slower because you're sitting there waiting for flash operations to complete each time, which means that if you're updating large numbers of devices, it becomes much slower. I've run that script, for example, updating like 200 devices over Bluetooth. And if I was waiting for each one of those to apply each time, it's going to take a long time. It's also not ideal for if you're trying to download like an image over CoAP or something over LTE, because it means your LTE connection is alive for longer. Yeah, you can, yes. I haven't implemented it that way, but there's nothing stopping the encoding from doing that. Yep.
Will we store the patch file in slot 1?
Yes. So if you knew that a part of slot 1 would never be used, then you could store it there. But if you know it's never going to be used, then reserving it in a separate flash thing doesn't really cost you anything. In fact, it saves you, because if you know that a certain area in slot 1 is never going to be used and you can use it for the patch file, that also means it's never going to be used in slot 0, right? So you're reserving memory in slot 0 and 1 rather than just reserving that memory in a dedicated area.
Let's say that for a lot of applications, we have just an external flash chip because it's useful for other apps and other program settings and logging of data and stuff like that. And then it's a trivial amount of that space for the external flash. So we find that pretty useful.
Yeah, that sort of comes back as well too. When the application's getting complex, with like a 9151 doesn't have the most flash in the first place, you're running a Bluetooth stack and LTE stack, we can't actually fit the two images, we can't fit two slots in the onboard flash anyway. So if a second image is sitting on the second slot, reserving 64K of a 128 megabit flash chip is, you don't really care. No, that's it. Nope. Certainly not rigorously proved or proven or rigorously tested. It is something which we have observed to be true over many years of the sorts of applications that we develop. Whether that's true for the particular applications that you develop, may or may not be. But the general theory is the same for all the patching algorithms, right? Like if they didn't stay the same, then it wouldn't really work. Yeah.
Run the code, because you can download the code and run it yourself. And
There you go.
Yeah.
Yep. Colors?
Just briefly, the Fuse SDK that's, your SDK that includes code the embedded and the Python side of
It's two separate repos, but yeah, one is the Python tooling side you run on your PC, which was what I was running here. The other is our larger SDK side, which has CPatch as part of it. Yeah. Sort of. So it reverts to Apache 2.0 after 2 years. Up until that point, you can do whatever you want apart from you can't repackage it and charge people for it. So after 2 years, Apache, right now, do what you want, just don't sell it to other people. Because we want to do that.